This video is part of a course on food physics. The porous media framework, of which this video is part of the theory section of that course on food physics. And this section belongs to the governing equation for deformation, basically equations of mechanics, in particular poromechanics, that describes the deformation in food during processing. The immediately preceding video of this one, so you can see this, we are here, and the immediate preceding video would be just a general discussion on why model deformation, and the follow-up video is a continuation of this one because it's kind of long, so it goes into more details in the second one in developing the theory closer to the context of foods. Deformation belongs to the very well established subject area of solid mechanics. So to study deformation, we basically have to develop the equations in solid mechanics. Now we will start really slow, but I would like you to see, if we go at that pace, then developing the final equations for food is going to take like a whole semester. But we want to do this in little more than an hour. So there's going to be jumps, but we still would be starting very slow and defining basic quantities so that we have everyone on board. So we'll start from the very basic quantities of mechanics. So here we have a block that has a surface area A, and on which we have a load F that is applied, and the load is applied over the area A, so the stress would be given by sigma equal to force over area. Because of this load, this cube will deform, so it will compress in this case, and let's say the compression is of amount delta L. That's the deformation. And so strain is defined as this deformation divided by original length. And so these stress and strain are related by the material property, and the simplest of them is this linear elastic material that we know of. So stress over strain is the Young's modulus, E, or the modulus of elasticity. So in a complex material or a complex load, the deformation is going to be all over the place. It's going to vary in all kinds of ways. So we need to find a way to keep track of all these deformation. So for that, we define a quantity called deformation gradient. So we have a point here that because of the load, it moves the point over there. So deformation gradient provides this local deformation at a material point. So inside the material, we want to keep track of how the points moving in relation to the original location. So deformation gradient F is the derivative of each component of the deformation, the deformed x vector, with respect to each component of the reference x vector. So then for 1D, deformation gradient would be given by this, that the component of x vector in relation to the original reference x vector. So deformation gradient is a tensor quantity, and we're going to see how different loads affect deformation gradient. We're not going to again get into details of this, but you will see later on that the equations are formulated in a way that it is the deformation gradient that we solve for. So in the last slide, we discussed a deformation gradient that keeps track of the strains. Now here we want to define something that keeps track of what material it is. So this strain energy function kind of characterizes the material. So let's define this strain energy function for some very simple material. The idea of this extends to more complex material, and we will see that it is using this strain energy function that we will bring in different types of materials as we study different food materials. Okay, and so suppose we have a bar of length L and cross-sectional area of A, and then we apply a increasing force. So it starts from there and I keep increasing the force. So if I plot here force versus the displacement delta, the change in the size of the bar delta L, then for a linear elastic material, F will increase linearly with delta L, and the work done in extending by a small amount d delta L. So but for a small amount d delta L, the work done in extending is equal to, if I write dw prime is equal to F times d delta L. So this is good old work done is equal to force times distance. Now work done per unit volume would be divided by A times L, and so here also divided by A times L. So let's call this quantity as dw, and that is equal to F over A is the stress, and d delta L, sorry, so sigma times d epsilon, and what this means is I can write stress equal to dw over d epsilon. This is a very, very important relation. So this W is here work done per unit volume, and so this strain energy stored in an elastic material would be this work done, and therefore this is the strain energy. W is the strain energy, and so you can see that it depends. It's going to depend on the material. W, the amount of work that you have to do to put a strain of d epsilon, that will obviously depend on what type of material it is. And so therefore W can bring in the material aspect, the material behavior, and once we get the material behavior through W, from this relation I can always get the stress. So sigma is dW over d epsilon, and we're going to make use of this. Basically, we will bring in different food materials through different functions W, because different food materials would be storing different amount of energy for the same strain. So repeating what we did in the last slide, sigma is equal to dW over d epsilon, where W is the strain energy function, and it really comes from thermodynamics. So W can have very many complex expressions, but for the most simple material, a linear elastic material, we can try to see what is the form of this WA. So for an elastic material, then dW is sigma d epsilon here, and stress is related to the strain by the modulus, and so this is my Hooke's law, and then the strain energy function would be this quantity integrated between strain 0 to epsilon, so which is equal to half times E epsilon square. So this is the strain energy function for one type of material, that is for a linear elastic material. So for other materials, we have a lot more complex form for this W. The important thing is this relation is still valid, and we can bring in different values of different expressions for W to relate stress and strain for different materials. Okay, so the computation of this, the mechanics framework, it tend to get complex. I don't know about you, but suddenly it gets complex for me. And so it's nice to have an overview of the process of the mechanics or the framework or the computation and so on. So this slide is simply trying to give that overview. So first we need to determine what is the what are the driving forces. So for example, is it shrinkage, water loss, and shrinkage resulting from that? Is that the driving force, or is it a gas pressure that's forming? That's the driving force for swelling. Next, we have to characterize the material. So the strain energy density function, the one we just talked about in the previous slide, we need to get that for the particular material that we are interested in. Now, it often may not be possible to get everything exactly for the material. So we need to get it for something similar or that is very close. But we have to get this to relate the specific material or to apply to the specific material. So once we have the strain energy density function that characterizes the material, and this characterizes what is the load that's causing the deformation, then we can solve the governing equation. By solving the governing equation, we get that deformation gradient, which actually eventually gives us the displacement of the solid locations, the locations inside the solid, how do they move. So from that displacement, we can get velocity. And this is the velocity of the solid. And now we use that velocity of the solid in the transport equation, because in transport, So we include this as transport. In transport, we talk about how the fluid moves with respect to the solid, whereas this gives how the solid itself moves. So we combine these two. So what we are doing is we are combining the transport and the mechanics for a porous medium, and this is the subject of poromechanics. So we will slowly start to develop this governing equation. So let's bring in analogy from transport that many of you are familiar with. So governing equation for transport was combining some sort of conservation equation with rate law. And it's kind of the same idea here. So here we're trying to do solid mechanics and we're trying to get deformation in food. And so the relevant conservation equation here is conservation of linear momentum, which we'll describe in the next slide. That we combine with rate law. So rate law gives the stress-strain relationship, and for the simplest linear elastic material, this is like the Hooke's law. So conservation of linear momentum is really Newton's second law, which means the sum total of all the forces acting on the food, that is the surface forces plus volumetric forces, should be equal to the rate of change of momentum. So let's see how this momentum conservation equation leads to the equation that relates all the stresses and eventually to deformation. So to develop the equation for stresses, we will do what's called a control volume analysis. So we take a control volume of dimensions delta x, delta y, delta z. It's a cube, let's say, and the cube is filled with material of density rho, and its mass is m, and it's single phase. So we're not getting into porous media yet. So on this cube, we're going to say that the net force acting on the cube is going to lead to a change of momentum. And so let's do the detailed derivation. So before we do that, we need to define things nicely. So sigma, let's say x, z, this is the convention we'll follow. So the first letter is the direction of the force. So direction of force. And the second letter is the direction normal to the area, on which the force is acting. Okay, so with that, let's look at the stresses. So here on this face is sigma xx, because the force with the stress we're thinking of is in the x direction, and then the area, that's this face, direction for the area is perpendicular to the area, so that's also in the x direction. Now for simplicity, we're going to only do a force balance in the x direction. So in the x direction, there will be 6 different forces that we need to consider. One is these 2 faces, and likewise in the other 4 faces in the other 2 directions. And so we're doing this force balance and the change of momentum over time delta t. So notice that if sigma xx is the stress here, and then on this face, delta x apart, it's not going to be the same in general. So in general, we can write this on this face as the rate at which things are changing. That's del sigma xx del x times del x. That's the amount of change. So that change plus the original. So then on this face, it's sigma xx plus del sigma xx del x times delta x. Likewise, so let's write that down. So then the net force in the x direction would be sigma xx plus the additional quantity. So this is at x plus delta x times area, because that is the stress. And so that's the force, and the force acting over time delta t is going to lead to the change in momentum. So the net force is going to be all of these on the right face minus the same quantity on the left face. And so they are all in the x direction. Likewise, if we consider this guy, so which is on this face here, so this is also force in the x direction, but on the surface that has a normal in the y direction. So it's in a similar way we write on this face and on this face. So on this face would be whatever is here plus the change over delta y. So sigma xy plus del sigma y del y times del y times, that's the stress, times the area of this face, which is delta x times delta z times delta t, and minus the one at the back. Okay, and similarly for this one. So all of these together, all these terms together is what's called the surface forces. They're all acting on the surface of those cubes. So we need to do summation of forces, and so summation of forces would be surface force plus body force. What would be an example of body force? The simplest one is gravity. So let's say F0 is the body force per unit volume. So then the amount of body force acting is F0 times the volume. So that's the force, the body force acting times delta t. So now together these two we have included surface and body forces, and because these forces are acting over time delta t, they are going to lead to a change in linear momentum, or the net force is going to produce some acceleration. So the change in linear momentum is going to be it's the mass of the cube times its velocity at times t plus delta t minus the same at t. So the mass of the cube is delta x, delta y, delta z times rho. That's the mass times v, this whole thing at t plus delta t minus the same way. Okay, so now you see this delta x, delta y, delta z and delta t are there on both sides, and we need to cancel those and try to get to the differential form. So by dividing throughout by delta x, delta y, delta z, delta T, we get this, the first quantity here would be sigma xx plus del x of sigma xx minus sigma xx. So these cancel out, so we get these terms remaining. So that's what this one is. And likewise for the other faces. And finally, the body force. And on the right hand side, we'll have rho times v at t plus delta t minus. So that gives me the derivative of rho v. Note that this is a substantial derivative, meaning it's more than just the time effect. Nevertheless, this is not what we will be dealing with, because we are mostly going to be talking about what's called a quasi steady state. So we're not going to be dealing with accelerating elements in the food. When the momentum conservation equation is extended to 3D, it's going to look like this in the written in nabla form. And note, as I was saying in the previous slide, two things. One is, in the food, like in drawing, the deformation gradually develops, and it happens relatively slowly. So inertia is very small and can be ignored. This is the quasi-static loading condition. And this is generally the case for food processing. Secondly, most of the time the food does not have bulk motion like translation. Things are jumping away. We're not going to be solving for that kind of a problem. So then the acceleration also will not be there. And so with those two together, we can ignore this term. So this term is equal to 0. And so then the final equation looks like this, that relates the surface forces and the body forces. Now note that this equation is still written for a single phase solid. We will learn about extending it to the porous medium next. That's not done yet. So this is for a single phase, but this is what's called the equation for equilibrium, and this is the most basic equation that we're going to use to develop our equations for poromechanics for a deforming food material. Now, we saw earlier that if we have an applied load here that develops stress in the solid, and those stresses are related by the equation for equilibrium that we just derived. So all this was for single phase. Note that if you apply that same kind of load to a porous medium that has solid skeleton, but it also has a fluid like water and gas, if you apply a load, it's going to be shared by the solid skeleton and the fluids. Okay, so it's going to be shared, which means the applied load is equal to effective stress on the solid skeleton and the average fluid pressure. So this is a very, very important equation here, that the load is now shared between the solid and the fluid. Now, the average fluid pressure in the porous media in this equation here is due to the fluid in the pore, the gas and the water. The average fluid pressure is calculated by the volume fraction based averages, weighted average between the different fluid phases. So if there's liquid and gas here, it will be a volume fraction based weighted average that will give the fluid pressure. That's what goes in here. So if you did the transport modules in this series, we talked about this averaging things over an REV, or a representative elementary volume. This has been defined in the introductory module for transport. And so just like transport, for stress also we do volume averaging over each phase. And so the volume average stress sigma bar is the sigma averaged over volume. Now if I separate out the solid and the fluid phases, so this first part is over solid phase, and then these are over all the fluid phases I, and then if I simply multiply and divide by Vs here, then what do I get? 1 over Vs and then sigma integrated over Vs. That's really the volume averaged stress on the solid, and then Vs over V, solid volume over total volume, that's the solid volume fraction. In the same way here, if I multiply and divide by Vi, then this quantity is the epsilon I, or the volume fraction of phase I, and then this part of it is sigma bar I, or the average stress over for one particular phase. And so then we note the fact that this stress on the fluid is the addition of hydrostatic and shear component. Since the shear component in the liquid is negligible, the hydrostatic component, or the fluid pressure, replaces the stress. And so here then we put in pressure instead of stress for the fluid part, and we note this epsilon s, which is the solid fraction. That's really just 1 minus phi, where phi is the porosity. So phi is porosity, and so 1 minus phi times sigma s bar minus phi times this other component for all the fluid phases. So this now we can write as a effective stress on solid. So notice this stress was over the solid part only. So sort of the area occupied by the solid. Now 1 minus phi times rho s is really the solid stress calculated over the entire area. So this is what we are calling as effective stress on solid. That's this one, sigma bar prime. Prime is hard to see. And then pore fluid pressure, PF. So pore fluid pressure is this saturation weighted by saturation, all the pressures, and of course multiplied by the volume fraction for the fluid. That's the porosity. This is the total porosity, so this gives me the pore fluid pressure. So now with this equation, we go back to the equation for equilibrium. Remember, we had derived the equation for equilibrium, and that it was for a single phase. But now we are applying that equation for equilibrium for the average stresses in a porous medium. So for the average stress, we substitute that equation. So we say del dot sigma bar prime and is equal to del PF. So basically we plugged in this part in here, and so that gave us these two terms. So what these are is, this equation relates stress on the solid to the pressure in the pore fluid. So stress on the solid is affected by the pore fluid pressure. So this is going to be the most important equation for poromechanics that we will further develop. So on the left side again we have the effective stress on solid, and right side we have the pressure on the fluid phases. So this part is a bit advanced, so feel free to skip if you'd like this slide, but it's talking about, instead of using the effective stress like the way we defined in the last slide, we transform it, we express it via another stress measure, also called Piola-Kirchhoff PK2 stress tensor. It is an alternative version of the stress, and the reason for doing this is to be able to solve the deformation equations numerically more easily, and we almost always solve it that way. So this stress is converted kind of into this one. So if we plug in this equation into our equation for equilibrium that we had in the previous slide, del dot the effective stress is equal to del PF. So we just simply plug that in here, and so this becomes my final equation. Now this is not exactly how we're going to use it. We are going to still massage it more and develop it further, but this equation basically relates, it gives us the stress in the solid in relation to fluid pressure, and we're going to further change it and kind of make it more easily applicable to food systems with few more changes.